Lessons learned about powder color from phosphate remediation testing. In our phosphate remediation tests, our best powders were always dark colored brown, but just because a powder was dark colored brown did not mean it would perform well. We're expecting the same results here. Here is a picture of the 8 ferric oxide samples tested along with their respective color codes. There were 3 flaws in this test protocol. Flaw number 1, surface areas of the nanopowders tested were not known. All these samples were basically phosphate performance failures from batches dating back to 2012. Second flaw was the thermal camera I used, which was a Milesy Android compatible unit. Had 2 problems. Number 1, the thermal imaging software would freeze for about 2 seconds when the temperature shot up immediately after ignition. Most interesting time of the reaction, but by the time the software caught up, the party was pretty much over. The second problem with the Milesy thermal camera was its 600 °C temperature ceiling, which, while 50 degrees higher than the comparable Fluke model, was still a good 600 to 700 degrees shy of the temperature ranges at which conventional thermite burns. The third flaw was that sample 8 was contaminated. More details later. Sample 1, Amazon's best. It's a one-size-fits-all solid micron grain size particle. This is what sample 1, Amazon's best, afterburn looks like. Along with being the biggest mass volumetrically, the unreacted ferric oxide linearly distributed on the exterior of the afterburn mass was also unique among the 8 samples tested. Sample number 2, SkySpring Nano. It's a solid particle, nanoscale grain size, plus or minus 30 nanometers, surface area plus or minus 30 meters squared per gram. This is what the sample 2 SkySpring Nano afterburn looks like. Sample 2 expelled enough force to break the mini terracotta pot. Notice the afterburn mass is not completely burned and is powder-like consistency. Sample number 3 is the lightest colored nanoporous particle, micron grain size powder. Sample 3 was the least reactive of all 8 samples tested, characterized by a thermetic reaction. Is thermetic a word? Made it up. So weak that only the top layer burned and the white magnesium strip afterburn residue was left undisturbed at the very location where it fell. Next up, sample 4, the second lightest colored nanoporous particle tested. This is what the sample 4 afterburn looked like. Notice that marginally more of the top layer powder appears to have burned, and that the force of the reaction displaced portions of the white magnesium strip band residue. Next up, the sample 5 nanoporous powder. Sample 5, again, displays a marginally improved reaction to its immediate predecessor. Next up, sample 6 nanoporous powder. The sample 6 afterburn is approximately 50% molten, 50% unreacted powder. The penultimate sample is sample 7 nanoporous powder. The sample 7 afterburn is approximately 70% molten, 30% unreacted powder. Last up, our darkest colored nanoporous particle. Sample 8 afterburn displays as a solid mass with a powdered texture surface. A reason sample 8 was not molten was because the mixture had gotten moist, and this moisture presented itself at 2 times. The first time was pre-ignition, when it took significantly less volume of Fe2O3 to reach the required weight ratio. The second time was after ignition, where significant volumes of powder ignited well outside the diameter of the mini terracotta pot. Lessons learned in this video. There were 3. Lesson 1, we won't be using the Millsy thermal camera in future videos due to its technical limitations. Lesson 2, thermite should be ignited from the bottom of the powder mass, not the top as done in this video. And lesson number 3, storing ferric oxide in a desiccant dramatically improves thermite's energetic yield. When ferric oxide is not stored in a desiccant, energy expended burning moisture off the ferric oxide powder is energy wasted. In the next video, we'll begin experimenting with different oxidizer particle architectures to optimize energetic yield.